This is my view I use to explain myself how an aircraft wing produces lift. For some time, I try to wrap my head around the official explanations that are being used in aircraft designs and manufacturing and engineering. So, since that type of explanation works, that means that's the official explanation. If you are enrolled into a flying program, you go with those type of theories. It's like when Bohr came out with the atomic model, and the scientific community adopted the model because it can be tested in real life. Then all the designs after that were based on that model, and seems that the world did not collapse, and we have advanced technologies based on that theory. But now with the quantum theory, things are going to change a little bit, and we discovered that the atom is not really the way it was believed. Same thing with other theories. It doesn't mean if they work into certain designs, doesn't mean is that the theory explain the phenomena in a depth. So this is my point of view. It's not nothing that you need to take in consideration. I'll put it out there just because I have it. So we'll start with an arrow. So you have a person with a bow and arrow. So arrow goes sliding through the air, and you have some clumped up molecules here at the tip of the arrow, and you have the air molecules that are passing by, or the other way around, depends of how you set your reference point. The arrow goes through those molecules. So here you may have a little bit of higher pressure. If you have a bigger arrow tip, you will have more molecules gathering together momentarily, and the air is going to try to fly over, or this is, you can say, this is splicing the air, or is cutting through the air. So the air molecules go backwards, and you might have a little depression, little vacuum around here, but not much. And according to the Venturi, um, it's a very similar. You see this shape here, okay, and it's just a kind of a inside out. So you have some airflow or fluid flow moving here. When it goes to a compressed area or a smaller section, it will increase the pressure and the speed. So when you increase the pressure and the speed, the temperature change as well. But once it passes to this bottleneck, the air reduces the pressure, and you will have some sort of a vacuum around here. Same thing here. You have this arrow moving through the air, and some vacuum is going to uh, kind of pull the surface of this arrow. So the arrow in section is circular, and the air molecules, the vacuum actually, is going to try to pull this one in all directions, up, down. So the arrow itself has a center of gravity, and the gravity forces that pulls everything down. But also the air molecules have some properties. So have some inertia, some cohesion resulting in some friction forces, and it's part of the nature, the way everything was designed. So we don't know if what was first, the birds or the air first. So whoever designed the world probably took in account everything that should work together. The air molecules, then the birds flying through the air. So let's ignore the Darwin theory and think from different perspective. So now we have this arrow being pulled in all directions. And guess what? If this force is bigger than the sum of the forces, because this is kind of canceling out, the forces up and sideways, they cancel each other out. So what's left here is the thrust, the force that had like the momentum that was given from the initial launch, converted into kinetic energy, and which in our case is a thrust, something that pulls this one this way, and of course the inertia, and the gravity. So slowly the gravity and the friction forces around here and around the rough surface of this material is going to bring this one down to earth. So you would have to increase the kinetic energy by pushing this one with higher force, or maybe increasing the inertia, the weight of the arrow, the aerodynamics. So you can do a couple of things, but sooner or later this will come down, pulled by the gravity. So if you think of this surface, that the lifting force, the vacuum created here by the movement of this one into the vacuum created about here, if you think of making a change, so you may think, okay, how about I make this one a surface that is like that. So the side forces are lower, the forces, vertical forces are higher, but then you have to deal with the gravity, right? The gravity that comes into play. So what you do, you design this kind of a flying plank, a piece of plywood. You use a high power compressed spring, you load this system and you release, and this one is going to fly through the air. So humans tried all sorts of contraptions for hundreds of years, because they tried to imitate the birds, and they thought, okay, I need some sort of a wing so I can kind of flap around. They did not understand the principle of flight, how the birds are flying through the air and maintaining lift, especially without flapping the wings. So that's the most important part, how you stay afloat without moving the wings. So because you can't really create a practical structure, an airplane with some hinged wings that would flap all the time, and I will explain why that one is not feasible. So you have this flying surface, you want to be a flying surface, and you make it out of a piece of plywood that in sectionals is kind of a rectangle with a bit of a sharp tip, and we call it in airplanes, we call it leading edge. It's made out of two words, leading because it's leading the way, and an edge, it's an edge, right? So simple like description of this part of the wing. And so this one is flying through the air, so I drew this one this way instead of drawing it to fly this way like an airplane wing. So I might touch the topic why. And this one is flying through the air and is encountering some resistance because the air molecules are clumped up here, like they gather up here momentarily. So you have higher pressure here. But once the airflow goes, right, is being deflected, the cohesion force of the air molecules will create a vacuum. So the molecules that go here will kind of call their friends. Okay, you come with me because we stick around. And the reason is that they don't want to leave an empty space. I mean, there are empty space between the air molecules, but they don't want to leave a large field of empty space. So that's the natural design. Otherwise, without this type of intermolecular forces, you would see the world in a different way. we would not be able to survive here because the air would either go into the cosmos, into the so the atmosphere would just disappear into the interstellar space, or if the forces were wrongly designed for each molecule, and I presented in another video that each molecule and atom has energy, is made out of energy with precise forces as a vector. So each molecule has very precise design, very precise force that together form our world in the way it is. So it's a very exact design based on very specific rules and laws. So to avoid the development of the vacuum about here, all the brothers and sisters molecules here are going to drag these things. So it's not only this movement of the wooden plank or this fake wing, but also how the molecule react. And so you will have some vacuum here that is going to create some lift, and the most lift you will get about here around the leading edge. So after a while you will just have a sliding surface through the air. So the way the kids are using their sleds on the snow or on the ice, same thing, this is going to slide, and you will have some friction forces that will try to stop this one from moving forward. And in the airplanes it's called drag, which keeps this one from moving forward. And also you have the gravity that is always there, which is proportional with the weight of the material, because it's a pulling force exerted by the earth, which is higher with a higher mass, higher object mass. And so you have a sliding action on both surfaces, and if you get any lift here, you will get the same amount of force that we don't call it lift here, but it's still an opposite direction lift, or it's a suction force. So if we call this one, if we see it as a suction force, sucking this wing up, in airplanes we call it lift, there is a sucking force pulling this one down on the bottom, and you will have some forces on the sides, but they are minimal because we don't make this one too thick. So now if we increase the size of this thing, then you will have more force pulling this one up. So I would say the forces here are a bit higher and they decrease. That's I would see it. And also the forces down are in a similar way, because this is a symmetrical structure. And these things will cancel each other out. So what you have is the remaining force of the gravity and the kinetic force, the kinetic energy that move this one to forward. So the end trajectory is going to be downwards towards the earth. And it's obvious, you've seen that. You throw rocks to the water, they will always go downwards towards the water, and you expect that because you learn that as a child. You know what happens when you throw a rock in the water. So again, lower pressure here, lower pressure here. That's the way the molecules are being designed and act according to their design. So we are designed in a certain way, we act according to our design. We have some minor freedom, but still we act according to our body design, the natural world design. We can't really go through the walls because that's the design. And so here we have higher pressure, lower pressure, that's obvious. Now we want to increase the lift, because that's the purpose when designing of an efficient airplane. You want something that keeps this one higher for longer, so you reduce the necessary power that you need to use in order to keep the airplane afloat. So how you increase the force up compared to the force, the downward force? So you need to use either an asymmetrical surface, or you need to do something about it. So what I'll go in the other extreme, when I have this same, instead of having the plank, the flying plank like that, I'm going to tilt it vertically, 90-degree vertically, but it's still a surface that moves through the wind like that. So you'll have a high pressure here, because this one is going to encounter lots of resistance. And I may touch the topic here about the boats. So the boats floating or flying through a fluid which is heavier, have a larger molecule, heavier molecules, and more dense, require, so because of the buoyancy. So here airplanes have buoyancy, but it's so small, it's negligible. In the water there is buoyancy, and also molecules inertia, there is gravity, and so there is an effect that the boaters use. So you have to have a minimum speed at which the boat is coming out of the water and is just going to skid. So it's called coming out of the hole. Same thing here, you have to have a minimum speed for this thing in order to stay afloat, otherwise it's going to sink. So that's, in airplanes, is called stall speed. So that's due to the inertia of the molecule, the density of the molecules. So imagine also people trying to walk on the water. You can't walk on the water because your speed, your motion through those air molecules, it's so slow. So the molecules have time to move around. But when you move fast enough, let's say you start running at very, very high speeds, or you remember how people skip rocks, so they throw rocks on the water and the rocks skipping the surface for a bit. That's because the water molecules are heavier and have some inertia, and the rock is too fast. So the flying of the rock above the water surface is that fast that does not make the rock sink. So same thing with flying through the air molecules. So here you have the wing that is vertical in this case, and when it's moving this way towards this direction, you have also the gravity, you have the thrust force or something, maybe an imaginary force, a spring or something, or even a piston here. So you will have higher pressure here, and the vacuum is going to be created here. If you move faster, the vacuum is going to be higher. So if you move very slow, the air molecules have inertia and need some time to fill the gap. So they will have no trouble to fill this space if you move this at very low speed. And even these air molecules here goes here, and everything fills the void, fill the empty space in order to have a balanced pressure. So pressure, it should be equal all around. But if you move this one fast enough, the air molecules need some time to fly and move around. Like I said, they have some inertia, and the higher the speed of this object is, the higher the vacuum. And this vacuum actually is trying to pull the wing this way, and the wing is trying to pull the air, so the vacuum created here is going to pull the air here. So the opposite force, my headphones just disconnected. So the opposite forces, so an action has a reaction. So the vacuum will pull this one, but the opposite force will pull the wing backwards. And if you see this resultant force of these micro forces here, the resultant force, you can call it lift, but this way. So in this case, it does not help, because you want the thing to fly and go vertical, not being pushed backwards. But these calculations are being used, or these forces are being used when they design the aircraft, and they are considered dragging force, and they call it drag. So that's the exaggerations, or the opposite situation when compared to the sliding of the wing through the air. But now let's do this thing in a intermediary kind of way. So instead of having a sliding wing through the air and not producing lift, or the lift would balance out the top and on the bottom, in this case the lift is maximum, right? Is maximum, so, but it's useless because you want this one to have some sort of a component that goes up. So let's change the component of the lift here and give half here, half there. So we have this 45-degree angle wing, and you see the forces, the component forces, and you have an action and reaction. So you have some a higher pressure molecule area here that is going to try to prevent the wing to move forward. So you need to have something like an engine or some force that is going to compensate this amount of resistance, which is part of the drag in the design of the airplane, is the drag. Also, you have the vacuum that is developed here. But what happens, so you have the airflow that comes from the top, and it's trying to compensate the vacuum here. So the vacuum is producing the lift like I described earlier. So, but the thing is here, once this one reaches certain area, it's going to fly away, because it's going to be pulled by the molecules in here. It's not going to continue the down pattern like that. And it will do at certain speed. It will do at certain speed, but when you consider air molecules inertia, which can be calculated, then you can calculate where about this one is going to detach from the surface. So the higher this angle, let's say if I make this thing like that, the closer to the leading edge is this deflection is going to be. So if you incline this one more horizontally, then this one tend to follow the surface for longer. Why? Because this has also cohesion with a surface, with a wing surface, and the vacuum created here is going to pull things from the around, but the opposite force, so the wing is pulling the atmosphere, and atmosphere with a reaction is pulling this one up, creating that lift that I was talking about earlier. So, but if you increase this angle, we call it angle of attack, that much, this is going to deflect sooner, right? So around the leading edge, leaving here sort of a not a lift like you expected here, not a lift. It's going to be some sort of a vortices. So I explained this one here. The easier visual is to look at the injection syringe. So if you have a syringe, like a thing that used to injection, vaccines these days are very common in people's heads. you pull the piston one way and you feel the vacuum, especially if the tip, the orifice of the where they are attaching the the needle is being closed or obstructed. So you feel the vacuum. So you pull one way and the vacuum pull the piston opposite way. But in this case, so here, if you pull fast enough, you see the vacuum stronger. So, but here, this one does not move as that fast. So this is a small device, but this one has a larger scale, cannot move that fast. If this one moves very, very, very fast through the air, you would create a vacuum here. And where you can see this effect on fighter jets. So fighter jets, when they move almost vertically, but in a horizontally, so vertical angle of attack and horizontal movement. Behind the wing, you will see kind of a steam because the changes into the air pressure, the vacuum, the high vacuum created here, create that type of a change into the vapor condition. So here, these air vortices are not acting together. So when you have, let's say, 10 people pulling a rope and all pull in the same direction at the same time, the resultant force is in one direction. It is coordinated force. But here, all these molecules are dumb, are just going around, not having a clear direction, which makes their individual forces, the small forces, not act in unison. So, not having a unison force causes this kind of a micro lift to be useless. So you have only the lift about here around the leading edge, but it's not enough to support the flying unless you use very high power engine, like I said, into the fighter jets. So now the better design that people came up with is a wing that it's sliding at the bottom. So you still have some sort of a sliding effect, sliding it through the molecules. So you have some higher pressure here, lower pressure here. So they are trying to deflect some kind of like that and like that. But because you see this angle here, this angle is not parallel. So this surface is not parallel with this surface. So this surface is sliding, but this one is not like that, but almost like that. But the air has time to float around the surface, and the vacuum created between the air layers and molecules here summed up create a higher force. So you see the lift force is not really vertical like we want to be to compensate the gravity. It's a bit backwards. So the fatter the wing here, the more backwards. So you don't want the wing to be too fat about here at the leading edge because it will encounter too much air resistance at the leading edge, and you may lose some air here due to a turbulence. And this has a component here, and this component will add up to the total drag on the aircraft structure. So the fix for that would be to increase the surface of the wing, so you make a larger wings, but that creates extra drag and extra weight that you have to carry around. So some aircrafts have very light wings and wider wings. But also there is a device, a little trick that helps this one to increase the lift. Is called flaps. It's a part of the wing, but it's increasing this angle here. So when you increase this angle, that means you have a situation compared to this, right? So you have some vacuum about here which create a force this way, which add to the whole wing structure force total lift. So the flaps structure is being used to increase the lift, and because it increases the lift, it helps the airplane to stay afloat at the lower speeds. So that's a different topic. I may not touch that one in the future, but that's kind of my easy explanation. So here I try to draw the airflow and how the airflow, that's a classic explanation, you find it in all the books, and why it's important to be aware of your angle of attack. So let you go half an hour in the video, and I will try to disable the comments, because those who learn through the official means, they will not agree with my explanation. Thank you and take care. Bye bye.